Hello, I'm Andy Rossi with Fujipoly America. As you may know, Fujipoly is a leading supplier of thermal interface materials. We offer thin film materials, putties, gap fillers, and very low modulus form-fitting materials. Gap fillers are used when there's an actual hard stop gap between the heat source and the heat sink. Because there are so many gap fillers available today, we wanted to demonstrate a quick and easy way to determine which is the best gap filler for your thermal application.
In this example, we've got a gap filler application where we've got a heat source and a heat sink. The heat source and the heat sink are separated by a 1.6 millimeter gap, plus or minus 0.2 millimeters. We've decided on a 2 millimeter material. The reason for that is that the 2 millimeter material will accommodate the max gap of 1.8, the nominal obviously of 1.6, but we'll also be able to get down to 1.4 millimeters, which is about 30% compression for the 200 GAE. At those compressions, we've got a force that can range from 16 psi at 1.8 millimeters. We'll have a nominal of about 25 psi, and if the gap is really small, at the other extreme of the compression, we're going to see about 40 psi. It's important to keep in mind that these forces will relax after about a minute, but these are the forces you're going to see during the initial installation. Next thing we're going to want to look at is actually the thermals. Obviously, that's what the material is there for. In this application, we've got a heat source, and what we're saying is the heat source is about 5 watts per square inch. That's one of the reasons we picked a GAE material, which is a much more cost-effective, lower-performing material. And these power densities should work pretty well with that material. So looking at the 200 GAE, we've got about a 1.5 degrees C in squared per watt thermal resistance. At power density of about 5 watts per square inch, we calculate about a 7.5 degrees C temperature delta between the heat source and the heat sink. It's important to remember that this is not the absolute temperature, but is the temperature gradient. The absolute temperature will be dependent on the heat sink that you're using and the ambient temperature. Okay. In this example, we used a 200 GA, which gave us a temperature gradient about 7.5. In some cases, that might not be good enough. We have several materials that range from, the GAE is about 1.3 watts per meter Kelvin, but we also have as high as 17 watts per meter Kelvin, which is only available through Fujipoly at this time. If we went to something like a 17 watt per meter Kelvin material, we would probably see a temperature gradient of about probably something about 1.5 degrees C as opposed to 7.5. The 200 XM, for example, has a thermal resistance of something in the ballpark of 0.27 degrees C in squared per watt. So it's definitely a material you want to look into if you got very high power densities, well above the 5 watts per square inch. Usually materials and usually requirements for XM or for power densities are easily in the 40-50 watts per square inch.